Welcome to the General Chemistry 2 class. This section is on chemical equilibrium. This lesson is about solving problems on chemical equilibrium, focusing on calculating equilibrium concentrations or partial pressures. Let's begin. In this lesson, we will calculate the equilibrium constant and the pressure or concentration of reactants or products in an equilibrium mixture. Here's the example number 1. To carry out the reaction, 1 mole hydrogen plus 1 mole iodine forming 2 moles hydrogen iodide. 0.20 molar each of hydrogen and iodine were introduced in a reaction vessel, and the mixture was heated to 150 degrees Celsius. Given that the equilibrium constant for the reaction is 140. Calculate the equilibrium concentrations of hydrogen, iodine, and hydrogen iodide. Solution. Solve the reaction quotient. First, since there is no product initially present in the vessel, the value of reaction quotient is 0, which is less than the value of the equilibrium constant. Consequently, the equilibrium shifts to the right towards the formation of hydrogen iodide. Let us now tabulate the concentrations. From the value of reaction quotient obtained, hydrogen and iodine are the substances consumed in the reaction until equilibrium is reached. Let X be the concentration of hydrogen consumed. Since hydrogen and iodine react with 1:1 mole ratio, X is also the concentration of iodine consumed. Take note of the negative change in the concentration of hydrogen and iodine since they are consumed. Meanwhile, the concentration of hydrogen iodide increased by 2 times. At equilibrium, the concentrations of the reactants are both 0.20 molar minus X. For hydrogen iodide, it is 2 times. Writing the constant equilibrium expression for the reaction. Substitute the equilibrium concentration values that we established. One approach to solve the problem is by taking the square root of both sides. This step yields two possible roots, the positive and the negative roots. Again, K expression is a ratio of concentrations or partial pressures. This ratio is always positive. Thus, we will neglect the negative root. By applying methods for solving algebraic equations, we find X to be equal to 0.171 molar. Substitute X in our expressions for the equilibrium concentrations of hydrogen, iodine, and hydrogen iodide. This will give us the following equilibrium concentrations for hydrogen: 0.029 molar, for iodine 0.029 molar, hydrogen iodide is equal to 0.342 molar. Example number 2. A container initially contains phosphorus pentachloride with a pressure of 0.800 atmosphere at 350 Kelvin, and the following reaction took place. Phosphorus pentachloride forming phosphorus trichloride and chlorine. Calculate the equilibrium partial pressures of phosphorus pentachloride, phosphorus trichloride, and chlorine if Kp is equal to 5.81 times 10 raised to the negative 5. Solution. By inspection, we can see that the reaction quotient Qp is 0, which is lower than Kp. With this, the equilibrium shifts to the right or towards the formation of phosphorus trichloride and chlorine. Let us construct the table to establish expressions for the equilibrium partial pressures. Initially, phosphorus pentachloride is the only substance present, with a partial pressure of 0.800 atmosphere. Let X be the pressure of either product formed with this. The change in partial pressure of phosphorus pentachloride is negative X. Meanwhile, the partial pressure of phosphorus trichloride and chlorine increases by X. Thus, the equilibrium partial pressures are as follows. For phosphorus pentachloride, 0.800 atmosphere, negative X. For phosphorus trichloride, X. For chlorine, X. Write the Kp expression for the reaction. Substitute the equilibrium partial pressures we have established in some cases. The value of X is too small compared to the initial concentration or partial pressure. As a rule of thumb, the added or subtracted X can be neglected when the ratio of the initial concentration partial pressure to the K value is greater than 1000. For instance, to determine if we can neglect X in the expression 0.800 negative X in the denominator, divide 0.800 by the given Kp since the ratio is 1.38 times 10 raised to 4, which is greater than 1000. X can be neglected in the denominator. Solving for X in the simplified equation, we get X is equal to 0.00682 atmosphere. Substitute X in the expressions for the equilibrium partial pressures. For phosphorus pentachloride, 0.793 atmosphere. For phosphorus trichloride, 0.00682 atmosphere. For chlorine, 0.00682 atmosphere. Example number 3. To investigate the reaction in example number 5, a vessel was filled with 0.100 m each of nitrogen dioxide and dinitrogen tetroxide, and the temperature was maintained at 25 degrees Celsius. Calculate the equilibrium concentrations of nitrogen dioxide and dinitrogen tetroxide, considering that the value of Kc is 3.1. Conclusion. Write the QC for the reaction. Substituting the given values, we obtain QZ is equals to 10, which is greater than Kc. With this, the equilibrium shifts to the left. That is, the nitrogen tetroxide is consumed until equilibrium is reached. Tabulate the concentrations. Initially, the reaction mixture consists of 0.100 molar nitrogen dioxide and 0.100 molar dinitrogen tetroxide since the shift of equilibrium is to the left. The concentration of the nitrogen tetroxide is reduced while the concentration of nitrogen dioxide is increased. Let X be concentration of the nitrogen tetroxide consumed in effect. The concentration of nitrogen dioxide added is 2 times. Take note that change in concentration of the nitrogen tetroxide has a negative sign since it is consumed in the process, and that of nitrogen dioxide has positive sign as a result of increase in concentration. Thus, the equilibrium concentrations for nitrogen dioxide and the nitrogen tetroxide are 0.100 molar plus 2 times and 0.100 molar minus X, respectively. Write the Kc expression for the reaction. Substitute the equilibrium concentrations we established. Let us try if we can simplify the denominator on the right side of the equation. Our criterion for neglecting X is that the ratio of the concentration to the Kc must be greater than 1000. In our example, the ratio is less than 1000. Thus, X cannot be neglected in the denominator. Simplifying our working equation leads us to a quadratic equation which can be solved using the quadratic formula. For a quadratic equation of the form ax squared plus minus x plus c equals 0. The values of x can be calculated using the quadratic formula x equals negative b plus or minus square root of the quantity b squared minus 4ac all over 2a. Since a quadratic equation has two possible values of x, choose the one that gives positive values of equilibrium concentrations or partial pressures. Substituting the values of a, b, and c to the quadratic formula, we obtained x is equal to 0.0268 molar or x equals negative 0.207 molar. Let us discard the second value since concentrations cannot be negative. Thus, we will use x equals 0.0268 molar in our calculations. Plugging in the value of x in the expressions for the equilibrium concentrations of nitrogen dioxide and the nitrogen tetroxide, we get nitrogen dioxide concentrations is equal to 0.153 molar and the nitrogen tetroxide is equal to 0.073 molar. Summarize, in calculating equilibrium concentrations, determine first the reaction quotient to determine the shift of the equilibrium. Then, establish an expression for the equilibrium concentrations or partial pressures in terms of the change in concentration or partial pressure. Next, use the equilibrium constant equation solve for the unknown variable. Lastly, use the calculated value of the unknown variable to solve for the equilibrium concentrations or partial pressures.